Okay, so this is the outline of chapter 28. So first of all, we will introduce what is magnetic field, or more precisely, we should call it a magnetic flux density. Magnetic flux density. Actually, in this textbook, it called it magnetic field. I don't try to correct it all the way because, yeah, I will miss something. So I just tell you at the beginning. Precisely, it should call magnetic flux density rather than magnetic fields. But in this textbook, it does not distinguish a magnetic flux density and a magnetic field. In electromagnetism, magnetic field should be the H field. Yeah, so that's another thing. But in this textbook, it does not appear. It does not appear. So yeah, so I just keep it. I just tell you, oh, it should be magnetic flux density at the beginning. So then next, we will talk about the cross field. If we have E field and B field, uniform E field and uniform B field perpendicular to each other, there will be some interesting phenomena. And then we'll also talk about an experiment called the Hall effect. So it tells you that the moving charge in the conductor should be negative charge. So this is one of the experiment to let you know, oh, so there should be something called electron. Yeah, at that time they still don't know, but yeah, they start to consider, oh, the moving charge in the conductor is not positive charge. At least they know this due to this experiment. And then they will talk about the circulating charge particle, and then the particle accelerator, and then magnetic force on a current carrying wire, and then the torque, and then magnetic dipole, which is quite similar to the electric dipole, but it is magnetic dipole. Okay, so here, talk about magnetic field. Okay, I repeat the final time, so it should call the magnetic flux density rather than magnetic field, but in this textbook, it all the way is called a magnetic field, so I just keep it like this. So usually I will just call it B field, so you don't mix up. Okay, so here, B field can be defined to be a vector quantity that exists when it exerts a force Fb on the charge moving with velocity. So here in this chapter, we try to introduce when there are moving charge in the B field, what will be the phenomenon. We don't know how to generate the B field yet. So in the next chapter, like chapter 29, we will consider how to calculate how much B field is generated by some structure, like some current. Yeah, maybe some current loop to generate the B field. And also in chapter 30, things may becomes more complicated, which is like if there are some changing magnetic flux, there was some changing magnetic flux, it will generate some E field. Changing magnetic flux for a coil, then it will generate E field. And also, if there are some changing E field, it will also generate B field. Okay, which will be covered slightly later in chapter 32. But anyway, in this chapter, we just pretend there are some mechanics to generate the B field. Then we try to consider the interaction between the B field and the moving charge. Okay, so here is the claim. Okay, so it's just like B is Fb over Q times V. So at the beginning of this semester, we learn about the Coulomb's force, which is like F equals K times Q1, Q2, and then over R squared. So at that time, we just assume that the Q1, Q2 are just stationary. They just place there, and then if there are two charge, no matter they are positive charge or negative charge, there will be force acting on each other. So if they have the same sign, then they will repel each other. Otherwise, they will just attract each other. So here, suppose we have a B field, then there will be some force acting on the moving charge. So this is the charge amount. This is the velocity. This is the velocity of the charge. We assume the charge is moving in a constant speed, constant velocity, and then, okay, so this force will be related to the charge amount. So very makes sense. This is also related to the charge amount. But here, it also related to the velocity of the charge, and also the B field, So if we try to write it in a vector form, it is like FB vector equals Q. Q is a scalar. V is a vector, and then B is also vector. So we cannot just place them together. So there is an operator between them. This is called the cross product. I suppose in high school physics you should have learned about this, but actually we will just repeat it again. So here, for the magnetic flux density, I mean the B field, the SI unit is called Tesla. So nowadays you are familiar with the Tesla, but in another sense, which is the company of Elon Musk. But yeah, actually, it is named Elon Musk due to this guy. So this guy invented the AC power. Yeah, actually invented AC power. And actually, the Edison invented DC power. Yeah, at that time. Okay, so here we have a cross product, and later we will talk about how to consider the direction of the cross product. So, and actually this one is called the Lorentz force. Lorentz force. Okay, so this is called the Lorentz force, which is the force generated by the B field to a moving charge. Okay, and yeah, so here is a scalar form, so you can still see FB, QVB there, but we have a sign of phi here. So phi is the angle between the V and B, but with a sign. If it is something like dot product, then you multiply by a cosine theta rather than sine. But here, this is a cross product. So rather than multiplying the cosine of the angle between them, we multiply the sine of the angle between them. Okay, so, well, okay, so, yeah. So here, we try to talk about how to determine the direction of the cross product. Okay, so here in figure A, we assume that V points to this direction and B points to another direction. So we try to use our four fingers, point to the direction of V, and then we try to cross to B. Yeah, so in this case, your thumb will point to the direction. So you just try to you just try to point to this direction of V, and then you try to sweep it to the B. So here we have a V cross B. So you point to this direction first, and then cross to the second vector, and then your thumb will point to V cross B. So this is how the cross product work. And one thing to know is that maybe you can also consider, can I just point to V like this, and then I just rotate for more than 180 degrees, so I get the V cross B in the opposite direction. But yeah, you need to make sure that how you rotate this angle should be, this angle phi should be between 0 degree and 180 degree. So don't try to make it like 270 degree, or maybe this one is 300 and something degree. So then you will determine the direction of the cross product incorrectly. Okay, so this is simply the cross product. I suppose you should have learned it in high school. Yeah, so actually we call it right hand rule. Yeah, we always determine the direction using right hand. Yeah, if you just use left hand rule, then yeah, all the equations should have a negative sign. So here we keep all the formula using the right hand rule, rather than sometimes I use right hand, sometimes I use left hand, then you cannot remember when I should use which hand. So we always use right hand to determine the direction of the vector. Okay, so here we slightly talk about the cross product. Yeah, so for the cross product, it is like this is V, this is B. Okay, so this is the angle phi. Okay, and this. Okay, this thing. So yeah, so suppose V and B points to different direction. Maybe if they can also point to the same direction, and then it turns out to be a zero vector. So suppose they point to the different direction, and then they start from the same point. Okay, so here V cross B should be like V points to this direction and then cross to B. So V cross B should be pointing out of the page. So when we consider a vector pointing out of the page, we use a dot, a dot inside a circle to represent that this vector is out of the page. Out of the page. If we use a cross inside the circle, then which means that this angle is into the page, into the page for this one. Okay, so this is out of the page. Okay, so we know V cross B. Okay, so this is V cross B, or maybe you can, yeah. Okay, so actually this is actually the magnitude of V cross B. So in this figure, what kind of variable can represent V cross B, which is actually the area of this parallelogram. So suppose we have a two vector pointing to two directions, and then we try to draw a line parallel to B, and then this is another line parallel to V. So this parallelogram will have the area of V cross B. So this is the area equals V cross B, the magnitude of V cross B, because V cross B is a vector. And then we try to take the magnitude, take the absolute value, it's like take the magnitude, then it is the area. It is the area of this parallelogram. Okay, because in high school mathematics, when you learn the trigonometry, you know this triangle will have the area of 1/2 A times B times sine of C, something like that. Yeah. So this is one side, this is another side, and then times this angle, then it will be the area of the triangle. So this parallelogram will have the 2 times the area of the triangle. So yeah, so it just cancel out this 1/2 vector. So which becomes a v times b times sine of theta. So compare with dot product. Dot product is something like a dot b equals ab cosine of theta. So which is like if we have this is vector A, this is vector B. So it is like we try to project this A vector to the B vector. We try to draw a line perpendicular to B, to OB, maybe like OB. Then yeah, so this is theta. So this one is like this is A. So this one will be A times cosine of theta. Yeah, something like this. Okay, and then we multiply also by the magnitude of B, so that it becomes A times B times cosine of theta. Okay. So here we have quick check point. So let's see. So the figure shows 3 situations in which a charged particle with velocity v travels through a uniform magnitude B field. So in each situation, which is the direction of the magnetic force or the Lorentz force on the particle. Okay, so for the first one, we point to negative x-axis, B point to negative y-axis. So this is positive x, positive y, positive c. So we point to negative x-axis, B point to negative y-axis. So what is the direction of v cross b? Anyone can answer. Anyone want to answer? To positive C or negative C? Let me see. Oh, negative C. Okay, any other opinion? So I draw the blue arrow pointing to the positive x, positive y, and positive c. So which direction is v cross b? Any other? He said negative c. Any other opinion?
Positive.
Oh, is it you? And then, maybe you answer simultaneously. So I don't. Yeah. Yeah. Actually, this is positive z axis. Yeah. Maybe if you just answer at the same time. So maybe I just mark which one is here. Okay. So actually, this is like v cross b. So points to the positive z direction. And then, yeah, for BC, let me go quickly. So, we pointing negative y direction, and then B. E is negative c. So this is positive x direction. Okay. Wait a sec. Negative, positive c. E cross B, yeah, should be positive x direction. E cross B, yes. And then for the C, they point to the opposite direction. So this is a zero vector. So there is no direction. So this is a zero vector. Zero vector. Okay, so yeah, maybe maybe I just mark it down. Before we move forward, I will just supplement the calculation of unit vector. Unit vector for cross product. Okay, so just in case I forgot next time. Okay, so let us stop here today.